Yes. Okay. Okay, so I will start, it's a crash course on Fermionic variables. So take n objects. These are, you can think of them as anything, abstract objects, abstract generators. You can, these objects could be differential forms. You can choose them, if you choose correctly, as set of matrices, but you can just take them as totally abstract objects, apples. So there could be differential forms. You can realize them using matrices. So we want to define operations on these objects. So first we want to construct a vector space. So we want to multiply them by real numbers, and we want to sum them. So I can define, I can multiply one of these generators by some real constant, and I can sum two of them. So if I put together these two operations, then I can construct a vector space generated by these n objects. And now I want to multiply two of these objects together with some group. So I multiply them, kj, kk, and what I require is that this product anticommutes. So I want that kj, kk equals minus kk, kj, and in particular, if I take the square of any such variable, the square equals 3. Okay, once I have these operations, now I can construct any polynomial with real coefficients in these variables. And since the square of any of such objects is 0, such a polynomial can have degree 0 or 1 in each variable. Because each time you have a higher degree, you can always reorganize that to have this term. So now I define the Grassmann algebra, actually real Grassmann algebra, generated by these n objects. So we call it G R Chi1 Chi n, and that's the set of all polynomials in Chi1 Chi n with real coefficients. And in particular, since the square of each variable is 0, the polynomial can have degree 0 or 1 in each variable, in each chi. So there are not so many of them. All these, you can take these as really just a list of rules. So if I take now some element in this algebra, maybe have something here. So take D in G n, where I can decompose it into a polynomial degree 0, polynomial degree 1, and so on in each variable. So the polynomial of degree 0 is just a real variable, a real number. So this is a real number. Then I'm taking polynomials of degree 1. I can take a polynomial of degree 1 in each separate variable. So I have a sum of chi j times eventually some real number, vj. And I will call it 1 because I have a degree 1. And then I go on. Let's take polynomials of degree 2. So here I have the sum over two indices. Here I have chi j, chi k, d2, jk. Already here I have to be a bit careful. You see, well, first, if I take j equal k, that's 0. So certainly these two numbers are different. So here certainly j is different from k. Second remark, if I exchange these two, I have the same polynomial, but I pick up a minus sign. So if I want to avoid problems here, I better choose this object to be antisymmetric matrix. So I have to require d jk to be equal to minus dkj. And then I have no ambiguity. Or I have to decide from the very beginning, I will pick up a fixed order. I don't want to count the same object many times. And then I go on. Then I will have a v jkl, v3 jkl, jkl, and I go on. And how much can I go on? Well, at most I can have one time, once chi1, once chi2, once chi3, and so on. So at most I can put one of each generator. The moment I put one more, I get 0. So the very last term will be Vn, and here I don't have to put even indices because there is just one number, chi1, chi2, chi n. And I stop here. Oops. So what else do I need? Yeah. So and the other ingredient we will need later is a special subset of these elements. So take the elements where we only take terms here of even degree. So I don't have this term, I don't have the term of order 3, I just have the zeros, term of order 2, and so on. So I call these G even. So this is a set of polynomials of even degree. Now, these objects have special additional properties. So if I take two elements in G even, well, they have the nice feature that they commute. V prime equals V prime. You can see it easily if you take chi1, chi2 could be one of such elements. Chi3, chi4 is another. When I want to exchange them, I have to take chi3 and you must jump twice. So I pick up twice a minus 1, so it's plus. And the same for chi4. So this is chi3, chi4, chi1, and so on. The only thing is that still, even if they commute, they are not real numbers. If I take the square of this object, it's 0. Why? Because now I can send chi1 here with minus chi1 square, chi2 square, and that's 0. Okay? And the last thing, if I multiply two objects that are just in the even subset, well, I still get an even number of terms. It's still even. So this is a subalgebra. Yes?
So I'm a little bit uncomfortable not having a representation of this algebra. So where will be a simple representation of it?
For instance, you could take 1/4. So this could be, you could take ij, you could see it as a dxj. And then chi j, chi k, this would be the exterior product. That's one possibility. Or you can choose appropriate, they are pretty horrible, but you can choose appropriate matrices. And you see matrices, the matrix product is not commutative. So you can choose a special set of matrices that anti-commute. For certain applications, so if you go to this paper, actually you will see this representation. Sometimes it's more useful if you want to have more general applications of these to keep the abstract notation. But you can always find you can always find a concrete representation. Okay, so the even is in subarticle. Okay, I think we have all we need. We need something else. Ah, yes. So if I take an element in this subalgebra, it always looks take G even, then I can always write V as, so V has a first term, polynomial of order 0, that's a real number, which I call V0, and then, well, then I have to start, I cannot take this, I start with a polynomial of degree 2 in the chi, and so on. But the moment I have some chi's, when I take enough powers, I will get 0. So what I have after V0, I call it n, and this object is a polynomial in the Grassmann variables, and it's nilpotent. So V0 is in R, and n is nilpotent. So there exists a k such that nk to the k is different from 0. Okay, and actually, if you want some notation, this here is called the body of this variable, and n is called the soul, because somehow it does not appear a concrete meaning. So, now that we have these, I can extend the notion of functions to even elements of a Grassmann algebra. So take, okay, now I have the same problem with that. Yes, functions. Take any functions on real numbers. Let's say C infinity, because I need C. Take f, which is C infinity of R. I can extend f, I can define f as a function that goes from G even to G even in the following way. Take any element in G even, so it will be body plus soul. I define f of v as a Taylor expansion sum over n from 0 to k. F, the else derivative of f computed at v0 divided by n factorial times n dn. So let's see, I stopped at k because this is the point where after which n to the k plus 1 is 0, so all other terms, we can write them, but they are 0. And what I wrote here, you see, is perfectly well defined. F is C infinity, so all these derivatives are fine. They are computed on a real number, so this is a real number. And what I have here is a product of even elements in the Grassmann algebra, so it's still in G even. So what I have here is indeed an element of G even. For example, what to do is the following. Write on the bottom of this. Let's take as an example. Take f to be the exponential function. Nice function. And take b, I take now something simple, just chi1, chi2. So this is an even element in the Grassmann algebra. The body of v is 0, and the nilpotent part is chi1, chi2. And actually this is very important. If I take the square, and square is already 0. Okay, now I want to define f of chi1, chi2. What would I do? Actually, exponential of chi1, chi2. Exponential of chi1, chi2. Well, I take the Taylor expansion around 0. And since n squared is 0, I just take the term of order 0, which is 1, and the first derivative, which is also 1. I just get this. Okay. And I can generalize this to here any even element in the Grassmann. Okay, and the very last, okay, now I have to work again. So the very last ingredient I need. So I defined an extension of functions, and now I have to define something that looks like an integration. Now, of course, I cannot integrate over the integral over real variables has a meaning in terms of surface or volumes. Here, I cannot give any meaning to this. It's just an operation that where I put inside a function of my Grassmann variables, and it will give me out, as a result a number, which is the integral. So I want to define the. I put this in quotation marks because it has nothing to do with the ordinary integral. So I define the integral over a Grassmann variable chi1 as a derivative. Yes. And this is okay, that's welcome in the world of Grassmann variables. And I will add this additional I require also that derivatives in different variables are still Grassmann in the sense that they anti-commute. So the derivative in chi1, derivative chi2 equals minus derivative chi2, derivative chi1. So let's take an example, which means that the integral of the constant function is the derivative of the constant function, that's 0, and the integral of the polynomial of order 1, derivative 1. So now that we have this, I can do another little example. I take the exponential. So in an example, we have defined the exponential of chi1, chi2. So now I want to compute the integral of this function. So I want to put the integral of the dk1, dk2 of the exponential of k1, k2. Okay, now we already know that this equals 1 plus k1, k2. So what I have here is the derivative in k1, derivative in k2 of 1 plus k1, k2. Well, the derivative of constant is 0, so we only have the second term. And here, if I want to take the derivative, I have to bring the variable next to the derivative. So here we have dk1, dk2, chi1, chi2. But to take this derivative first, I have to bring chi1 here. And yes, I didn't say that, but chi and the derivative anti-commute, so I pick up a minus sign. K1, dk2, k2. So I get minus 1. So the integral of this exponential function is equal to minus 1. It's just a sequence of rules, and you just apply this each time, yes.
In general, you will always find the real number, because
yeah, well, if I have here a function taking values from a real Grassmann algebra, yes. Okay, what you may ask is, suppose I could do the integral just over one variable. Then what I will get is an element in the Grassmann algebra, because I will still have chi2. If that was a question, yeah, you're right. So it depends on how many variables I integrate. So if I integrate only over chi2, I repeat the same game. I take as is. So I take as is. So I take just one derivative, and what I obtain is, sorry, I don't know. So then I just get chi2. So as you can think of the integral as an operation which will go and look in your sum where the variable appears, and it takes it out. So here the variable chi1 does not appear here, so I don't have it. Here it appears exactly this term, and the k1 is already in the front, so I just take it out.
So, in the representation with forms, that
If
makes
you
a
are-
little bit more sense, no?
Well, yeah, okay. then you are going from two forms to one form, so it actually, yeah, you're right. Then if you formulate in terms of forms, this is kind of a natural. Okay, now I have. Okay, so now that I have all these, we can try to start constructing a statistical mechanics theory.
Can I make a remark?
That's at the left.
Ah,
Yes.
please.
Margherita has a comment. So we have a comment.
Ah,
I have
yes.
a comment. This is what is usually called the rising calculus.
Yes.
Yes. And about 20 years ago, I published a paper with De Angelis and Sideralchus, in which we showed that you can give a probabilistic representation of this calculus completely.
Okay.
You have to use
These are-
Poisson processes, not Gaussian processes. And then you reproduce all the rules of the
Grassmann.
calculus.
Okay, I'd really like to know this reference.
It has been very useful in simulations, for example.
Can you repeat yourself, Gianni?
Huh?
Can you repeat
No, he
yourself?
said that he has a paper where they give a
20 years
probabilistic
ago,
interpretation of
Okay.
these Grassmann variables.
in which we gave a probabilistic representation of Grassmann calculus.
And I'd very much like to have the
Yes, well,
reference.
we will talk after.
Well, that's very interesting. I said that's one of the things that is always difficult because people ask, yeah, but is there any probabilistic interpretation? And I didn't know. Okay, so. So I will try to convince you that I can try to mimic what the notions of statistical mechanics when I also have fermionic variables. So as usual, well, I will put myself on the lattice and I will consider some cube or finite volume in ZE. I could do the same in any graph, but I need this to be finite. Just to make clear the mapping, I first write what we do for bosons and then what we do for bosons plus fermions. So, and hopefully so what would I do if I want to construct some statistical mechanics theory for bosons? Well, first I assign to the volume a spin configuration. So this is we call it, I try to remain consistent with last week, phi lambda, and this is a map, and now I take a spin with two components. So to every lattice point, you associate a vector, phi j, which has two components. Okay, now what do I do? Okay, now I should shift a little bit. same, but this time I write it in capital letter. Now this time my spin will be a vector where I have 2 real and 2 Grassmann variables. So the weight to write this space is R2, 2. And so to reach lattice point, I take a vector phi j, where psi eta, x, y, real, and psi eta Grassmann. And I do that at lattice point. Now, to construct an action for this, an energy for this spin configuration, I need to define first some kind of scalar product. I want to do a scalar product between different spins. So here, I have a very natural choice. The scalar product is the Euclidean scalar product. What do I do here? It's almost the same, but now I have phi prime. So I have the same for the real variables. But now I have to add something for the Grassmann variables, and the correct choice is to take psi eta prime minus eta psi prime. And I really need the minus. Why? Well, for instance, if I take the norm square of these, that's s squared, y squared. What do I have here? The first is the usual. But now, if I take psi equal eta, so what do I have? What to get is psi eta minus eta psi. But since this variable anticommutes, I change the order and you get 2 times psi eta. If I did not do that, then I would get 0. So now I can start defining an action. So for bosons, you have seen this action many times. I take S of phi, lambda, I take a quadratic part. I take phi, Laplace is phi. A mass part, 1/2 h, sum of j, phi j scalar phi j. This is what we saw last week. And then I add a quartic interaction. So the j, phi j square. This was the, I could write norm square, but it's better for the generalization to leave it as a scalar product. And so this depends on here in the beta. So here I have 3 parameters, h. So this is a 5-4 action. So what can I do on the other side? Well, I do exactly this, except that now my phi is replaced by this super vector, and the Euclidean scalar product is replaced by this supersymmetric scalar product. So I define S of eta hg lambda. So what we do, we replace phi with phi and scalar product with this new one. Okay, now you may be worried because
Margherita?
yes.
Sorry, is there a notion of positivity in the Grassmann variables?
Except for the body. If you take an even, because the only object which is that. So if you have, if I take an even element in the Grassmann algebra, I say that this, actually there I say this is positive, but what I mean is that the body, so the only real number that is there is positive. That's the only notion of positivity. By the way, actually I can define the inverse of an element in the Grassmann. Here I can define 1 over V, as long as the body is positive, exactly as for usual numbers. So if V0 is positive, then I can define 1 over V as the Taylor expansion.
Non-zero.
Probably just non-zero.
You're right, actually it doesn't need to be positive, it should be just different from zero. As for an ordinary number, you're right, thank you.
I mean, in a way,
Sorry?
via that kind of representation, at least the even guys really behave like infinitesimals. In some sense, your soul,
Yes.
the soul really behaves like an infinitesimal.
Yeah, you mean in the sense that
I mean, that's
it
kind of
corresponds to
what,
take then, when you have to take derivatives, that's,
well, and also when you look at this, like, when you sort of define the action of functions by this Taylor expansion,
Right.
I mean, it's in some sense.
so the K is like taking, yeah, it's true, the N is not taking derivatives too. So it's, yeah. Okay, now what was I? Yes, so, for the next backward. So if I want to write the probability
With
measure, I
that
have to study E minus
With
S.
that funny scalar product, do you still have sort of summation by part for the first term? Can you still write it as some sort of like non-square of a gradient?
No, I mean, you think of it as non-square, it actually,
Yeah,
no,
but
which is
okay,
why
but
I,
you
which
have
is why I keep
non-square.
it in this form. I mean,
Right.
this part is really a non-square,
Yeah,
but the
but
rest
this
is,
bit, okay, but
is
defining,
not a-
defining non-square as this,
Yes,
right? I mean,
yes,
so
then
you
it's
have
exactly the-
summation by part, I mean, so is this
yes,
equal to
yes,
also
you
the
can still do
scalar product?
integration by parts,
Okay,
absolutely,
that's fine.
yes. This is still a sum of gradients, yes. Ah, yes, sorry, didn't get there. So, yeah, and so, well, okay, I guess then, I don't know if you may get worried that this stuff, when I write it here, is not well defined. Why is it well defined? Because what I wrote here, I said, well, this S is, I just take this expression and I replace my super vectors. But what I get here is an even polynomial if my Grassmann variables. So if I have an even element, so what I get here is an even element in the Grassmann algebra, and for that we have seen that we can define functions. So when I write these, what I mean is that we should take the Taylor expansion of these around the volume. So these were defined.
Does it have to be even for you to be allowed to define functions to it?
Sorry?
Does it have to be even for you to be allowed to apply functions to it?
You can, I mean, formally I could define any, so I could define exponential chi
The order
as a
starts to-
Taylor expansion.
The order starts to matter, I suppose.
Sorry?
Then the order starts to matter.
Exactly. Actually, the problem is that then I cannot say, so as long as I have here something even, it has the same properties as the exponential. So exponential of v, exponential of prime, gives you exponential of v plus v prime. But here, if here I take just an odd element, then it's no longer two, but formally you can do it.
In abstract algebra language, you have a module with coefficients in the ring of functions, bosonic functions.
Okay, I believe you.
Can I make a quick comment while
Yes.
everyone's here? So Max coming in reminds me that we're going to move the time of this seminar to 3:30 to 4:30 instead of 3 till 4, because Max can't get here otherwise.
Yeah.
So next week it will be half an hour later, and so on.
Okay, so we are almost at the end of the construction. So to construct now a probability measure on these, well, if I was in the bosonic world, I take as d mu phi, sorry, I will just take d phi lambda e minus s phi lambda divided by z lambda, where z lambda is the partition function. And this d phi is the product of the d phi j, and this is the product of the deck measures. Now, if I do this in my boson plus fermion setting, then I define a new measure on phi. This time I have d phi lambda e minus s phi lambda, so everything is the same. But now I have to be careful because I'm not integrating over here, I'm integrating over R2 lambda. And here, so here we have the same, e minus s phi lambda, but here I'm integrating over R2 bar 2 lambda. The bar has to do with that I have two real and two Grassmann variables. And here I have a product over j d phi j, and that means dx dy side. And actually to get the right normalization I have to divide over 2pi. There is another convention where you define directly the integration of the Grassmann variable to have a 3-factor 1 over square root of 2. Okay. So, what are the differences here, apart from the fact that we have these strange variables? Now, what are the symmetries in this measure? Well, we have seen that this measure is constructed using Euclidean scalar products. So this measure, the action, everything is invariant if I do global Euclidean rotations. So this measure is invariant, just like invariant. And global rotations. Which means I send each spin to a rotating spin with the property where R is a linear transformation that conserves the scalar product. So R phi prime equals phi prime. Well, now I can go here and I can ask myself what are the symmetries in this measure. And it's the same. It's invariant. And the transformations where each spin is rotated, J, where R is a linear transformation that conserves this superproduct. R phi prime is phi prime. But now, what kind of rotations can we do here? Well, one possibility is to do, remember that we have 4 components. So one possibility is just to do a rotation on the xy path, and that's exactly the Euclidean rotation. So then I get back the rotations, and they act on xy only. But now there is a new symmetry. Actually, there are 2 new symmetries, but the important one is that there is a symmetry where I can exchange these 2 terms. I can exchange the real and the Grassmann part. So I mix xy inside. And now this is called a supersymmetric transformation. Or SUSY, normally for ability. And this is a new transformation compared to before. Now it may seem just a okay, it's well, okay, that's a new transformation, so what? Actually, this transformation has enormous consequences. If you have a function which is invariant under this kind of transformation, you have the analog of Cauchy's theorem. You can do the integral without really doing the integral. So, and this is the so-called localization
Margherita,
theorem.
could you write down one?
Sorry. Okay, so now I will certainly do a mess. So I have here a matrix, and I will break it into 4 blocks. This is a 2x2 block acting here, 2x2 block acting here, and this 2x2 block is acting here. Okay, now when I apply this, what I get is a psi y plus sigma psi eta. This is the first part of my vector, and below we get gamma xy plus b psi eta. Now, for example, let's take A to be the identity. So here I just get again xy and also b. And now here, well, I see immediately a problem. Here I will have a certain coefficients, and here I get a linear combination. But you see, this object must be the new x prime y prime. So it will not be real, but it will be an even element in my Grassmann algebra. So I need to have here something which is at least an even combination of Grassmann variables. And the only way to do it is to put here in this as elements of this matrix Grassmann variables. So sigma and gamma have as elements are Grassmann. So for example, I could take sigma is I don't know, alpha and beta, and these
So
are
now-
two new Grassmann
So
variables.
you're adding new ones, so that's not on the same.
Yeah, I have to
algebra.
actually extend my Grassmann algebra. Exactly. So
Okay.
normally what you have to
But
do is
so
from
now
the
on the
beginning.
larger Grassmann algebra, you don't put any sort of action or something.
No, I use the additional Grassmann variable objects, variables as parameters. You want more detailed? Let's
So I'm not understanding, you should get out 2 real numbers, no? No.
No, actually I've been cheating. The truth is that when I do this, I should accept the fact that this x and y are not just real numbers, they are even elements in the Grassmann algebra.
Okay.
The point is that when you do the integration, your function is smooth enough, you have no boundary terms, there is a certain number of conditions, but when you do the integral, then you can treat these two objects as if they were real numbers.
Yeah, because
So then they, yeah, go on.
yeah, even if they're under the integration, the integral knows what to do with the additional variables. It can be that the integral is invariant.
So I could be that here I have x plus n,
Mhm.
but when I do the integral, this piece goes away. And the reason is because, this piece will, when you put it into a function, it will correspond to derivatives of this function. And if you do your computations correctly, you discover that the contribution of this piece corresponds to a total derivative. So you write the integral of a total derivative.
So would I
It's
get the
a
same
boundary
result
term.
if I just forgot about that end?
Sorry?
Would I get the right result if I just forgot about the end from the beginning? No.
Yeah, well, when you do the integral, yes. If you're studying it as a function, no. The integral is a kind of erasing anything that is not a real variable. It's not totally trivial, I mean. The point is that if you do, you can actually define, which I didn't say. If I have a function of x, y, psi and eta, I should actually write here the integral dx, dy, d psi, eta. I can replace here f to be f of x plus n y's plus n prime. These are nilpotent terms, and that means that these will be f of x, y, psi and eta, plus eventually some derivatives. There will be a derivative in the first variable, and a derivative times, so there will be a derivative times n, and n2 n prime, the derivative in the second variable. Now, you can show, doing also then, okay, you can show that this will be down the integral, you will end up with the integral over a derivative. So if your function is 0 on the boundary of your domain, you have no contribution. If you have, you could have that you have more complicated, and depending on how complicated the expression is here, you may need that not just your function, but also a certain number of derivatives of the function are 0 on the boundary of your domain. But if you take your domain to be just the whole real R2, and you consider your function to be decaying with all the derivatives, then you have no problem. But if you do have actually a finite domain, then you have to be really be careful here.
Can I make a comment?
Yes.
So if you realize these Grassmann elements as differential forms, so this is a more general formalism which has advantages, but in the case where you have the same number of bosonic and fermionic variables, and dc and d eta are actually just dx and dy as differential forms, then this is ordinary integration of the same kind that is done in differential geometry with differential forms. So the two integrals that she's written there, you would just leave them out completely because the function that you're integrating is a differential form. And then it can be that you can find transformations that transform functions of x, which is a bosonic, which is one of the local coordinates, into a different. You can interchange, for example, x with differential forms in some of the integrals that, and it's a symmetry in some of the integrals that she's coming up with. Maybe.
More questions? Well, you can still ask questions. Or you can go back and say, no, you really didn't understand that part, go back. Okay. So I was trying to convince you that this additional symmetry, the one really mixing the real and the Grassmann variables, has important effects, and this is the so-called localization theory. Take a function of our spin configuration, which is of the form, I take a function only of scalar products for any pairs. And this f is infinity and fast decay. Then, actually, this is even too much, but with this we are safe. So then if I do the integral over r to 2 lambda of this function, what I get is the value of the function if I replace all the fields by 0.
Oh, so the first prime is a comma and the second prime is a prime.
That's right.
Wait,
G in the inner product.
phi j prime, and
Yeah,
for
yeah,
every pair j and j prime.
I think your point is one could also read it as phi j prime times phi j prime.
No, it's or if I call it phi j, comma phi k. Okay. Let's see a simple consequence of this. Let's take the partition function. Well, we have seen that the partition function is just made with this inner product, scalar product, they are a generalization, and it's invariant under its global rotations. So this is just the value of S and C, which is 1. So you don't need to compute the partition function. The partition function is always equal to 1 in a supersymmetric theory. And you have a zillion additional identities.
It's only true if you have exactly the same number of Grassmannian and bosons, or?
Yes, you need perfect grading. So you need the same number. Because, yeah, as far as I know, you need the same number of Grassmann variables and your variables. Okay, so now finally, we have
Well,
a
we've
few
been
minutes more. Just
interrupting. Why don't you go on for a little bit longer?
okay, just because I somehow now I would like to say what is the connection with stochastic processes. Yes, So I will say I call this SUSY statistical mechanics and connection with stochastic processes. So maybe I will give you just the first example, it's already very nice. So as first example, let's start with simple random walk, but it's in continuous time. So this is a continuous time process on our finite volume in ZD. And so if at time t I am at I, and I know the history up to time t, the probability that after an infinitesimal time I jump position j is given by beta delta t plus lower order corrections. So this process is Margherita. There is no vector. And they could take away this part because it doesn't depend on what happened in the past. So we have
J has to be neighbor of I.
you're right. So let's say, so now we try so, oh, just wait. any 2 points in my volume, and I will call LJT the local time at position J, so it's the total time spent at J up to time. And now I can consider the following average. So I consider the simple random walk starting at A, and I require that at time t will arrive in B, and I add here exponential minus h sum over j Lj of t. I could write here directly t, but it's kind of more general. It can be generalized. So now I can integrate over all times t. And the first remark is that this is just the inverse of the following matrix. I take minus beta de Laplacian plus h times the identity. I take the inverse of this between the points A and B. But there is more. This can also be written as the 2-point function of a supersymmetric model. So this is the integral over R to lambda of d phi. And here I just take S with beta h, but no quartic interaction. And I didn't finish, I need the 2-point function of this. So I have to add as an observable. This is the first component of my supervector at position A, first component of the supervector at position B. So it's the 2-point function of, and this is a Gaussian, super Gaussian. So actually this is a generalization of Gaussian integral.
Sorry,
I forgot something.
I have a stupid question. You sum over all j, the time spent at j up to time t, isn't
Yes.
that equal to t?
Yes.
Okay.
The reason why I wrote it in this way, because then you can generalize between different, but otherwise you're absolutely right. I would expect
Okay,
this.
great.
Yes. Good, you're following.
And in your integral here, shouldn't you remove the points A and B?
Sorry?
In your integral, that big integral down there, shouldn't you remove the points A and B? In the integral over the d phi lambda.
Here?
No,
No,
down.
here?
Yeah, here.
Yes. What?
Shouldn't you remove A and B
No.
from lambda?
No. No. It's really the 2-point function of Gaussian.
Oh, okay.
Is this
Yeah.
XA, XB here at the end?
Yes.
So it's dot products or just one
No,
component?
because these are actually just the first component.
First components.
These are 2 real
Yeah.
numbers. Even elements in the Grassmann algebra.
Got it. Right.
Actually, this is the generalization of the formula. Well, if I do phi, some matrix, phi, and phi has 2 real variables, x a, x b. This is modulo some one factor, and this is 1 over square root of the determinant times a inverse a b. Except that these will disappear because we have the Grassmann variables. They kill the determinant. Okay, and now
You mean it's the theorem above, the partition function is one?
The theorem below.
Oh, maybe it's gone.
sorry.
Oh,
Ah, yeah, there were 2 theorems. You're right. There was a localization theorem.
Down here, sorry, the theorem below, yeah.
Can I?
For me, yes.
Okay. at least to the formula Gordon Rule plus B. So, slightly more. Now, if I consider the 2-point function now for the weakly self-avoiding random walk, here I have exactly the same expression, but I have to add a small repulsive term. So if I take weakly self-avoiding random walk, then the 2-point function is again, I take the average for the simple random walk starting at A, I arrive at T at B, okay, so I write there like this, and this is minus G, here I have the sum over G, and this time I cannot add it in G squared. Okay, and now I integrate it in 0 and infinity, you see, and now I cannot write this as the inverse of a matrix, but there is still this mapping between the two integrals, except that now, here, lambda, what we have here is the action with a Gaussian part, but also the quoted. And there should be a G is fine. And I still have the 2-point function, so I still have x. Actually, you know that if I didn't have these, this would be totally impossible and meaningless. This expression is equal to 1. I need to do something to break the symmetry. Okay. So what we have here is a supersymmetric 5-4. Okay, I don't know, should I give the second example? The second example requires at least to define what is a...
You're continuing next week, right?
Maybe you continue next week. Do you want to do that, or are you here next week?
Yes, I'm still
You
here.
are.
Actually, it's the last week
Are you
I'm here.
willing to continue? Because you had a bit more. You wanted to talk about word identities and other things.
Yeah,
which
then I
think
could
would be
actually,
interesting.
yeah, then I
And it
could.
would solve my problem of who's going to.
Finding somebody.
Yeah, if that's okay.
Yeah,
Then I
that's
can give it, then because actually I didn't, then
Yeah,
there is
then
an
you
additional
can-
relation with other stochastic processes, certain history-dependent stochastic processes. So
Great.
maybe I can stop the recording.